Welcome back to C23 Classroom channel, and today I would like to share with you about the calculation of turbulent boundary layer by using the empirical form. So bear in mind that empirical form means that we need to calculate very detailed. But however, sometimes we cannot do this by on paper. So sometimes researcher will use a computer to solve all of this to simplify to accelerate their calculation. But basically, the idea is like this. So the empirical method of predicting turbulent flow quantities on a flat plate with zero pressure gradient is based entirely on data. It is more accurate than the power law form, but also more complicated. The time average turbulent velocity profile can be divided into two regions, the inner regions and the outer region. The velocity profile for the inner region is defined as u over u shear tau equal function of u tau y over kinematic viscosity nu. So the u shear stress here, u tau here is equal to tau naught mean shear stress that occur on the surface of flat plate divided by its density rho, and we give the power of 1 over 2, and we call this one as shear velocity. So another one, we have the velocity profile for outer region, and it could be defined as u minus u bar over u tau, which is the function of y over delta, and we call this u minus u bar is the velocity defect, means that the u here, u infinity, means the free stream velocity, it's equal to capital U. So it means that the free stream velocity will slow down when it's go through the area near the flat plate area, and that's why it has the velocity defect here, because the free stream velocity is slowing down. So if you have a textbook, you could see a lot of graph, but I want to say that for this graph only. So we could imagine that the velocity is quite it's not unstable and not easy to predict. So what we do is actually we make an empirical calculation. So we uh, simplify the curve that we have from the graph into a few curve fitting equation, and we get this equation that later on we will discuss. So to simplify this calculation for this syllabus, it is okay for us to understand that from all the calculation that I show you above, so and we plot a graph, we have a curve fitting line and so on and so forth, and finally we could say that we could propose a few relationship, and this relationship is the most excellent result that we can use in our calculation. So we could say that CD, which is the local coefficient of friction, or sometimes it's called local skin friction coefficient, is equal to 0.455 divided by ln 0.06 Reynolds number square here. So in this equation, you need to be very carefully, because the ln here, the natural logarithm here, is for 0.06 times Reynolds number. So means that you need to know what is its Reynolds number, multiply by 0.06, then you find the value of natural logarithm for this term. Then you need to square it. So and then for the drag coefficient, the total coefficient that occur for that flat plate, it can be assumed as CD equals 0.523 over ln 0.06 Reynolds number square. So again, I would like to remind you, so you need to solve this term first before you could get the value of ln here. So the difference between empirical method and power law form is power law form quite rough calculations, and it will give you a little bit error. It's around might be 2 to 4, 2 to might be less than 10% from the real one. But it is okay to use both of this method because turbulent boundary layer is quite rough. So the boundary layer thickness is not static at certain height. So it's different because the flow is turbulent. So and then this is the final equation that you need to understand, you need to remember to solve the boundary layer thickness here by knowing shear velocity u tau. So u over u tau is equal to 2.44 times ln u tau delta over nu, which is the kinematic velocity here. This is not velocity, this is the kinematic viscosity plus 7.4.